Okay, it's 5.1 now. So now we're doing the reverse of the derivative, the antiderivative. Okay. It's not a big deal. And you could kind of, if you get really good at, if you're already really good at taking derivatives, you'll also be good at taking finding the antiderivative. So in particular, what are we going to be doing here? Example, let's say big F of x. So I want to make sure I get my variables correct. Sorry, I didn't really. Big F of x is, no, let's start with little f of x, right? So little f of x, we'll say, is 4x cubed. Okay? We want to find the thing that resulted in this being its, so I think of it going up one level. So the derivative of what is equal to this thing here, okay? And if you think about it for a second, it's this guy. If you took the derivative of this, you would get this. That's what we're after. Another example, maybe a trig example. The derivative of what is equal to cosine of x? Well, the derivative of cosine of x is, sorry, the derivative of sine of x is cosine x. So it's this reversal process, and yeah, that's what we're after. Okay, so we'll call it the antiderivative here at first. Antiderivative. We could make a definition for it, and usually we'll call the antiderivative big F if the derivative is the original function is little f, the antiderivative big F. So we'll say a function big F is an antiderivative of little f on an interval I when f prime of x, the derivative of big F of x, is equal to little f of x for all x in that interval. Okay, so again, let's look at maybe another example. We'll say little f of x equals 5x to the fourth. Then, so if little f of x equals 5x to the fourth, then big F of x must be equal to x to the fifth because its derivative of this is equal to this, right? So because f prime, big F prime of x is equal to 5x to the fourth, which is equal to little f of x. Okay. One thing to note is that if this big F of x is the antiderivative, then you're kind of left with an implication there. If big F of x is the antiderivative, sort of the implicit idea here is that big F of x is differentiable. And not only is that going to be true, but then if you have differentiability, you have continuity. Okay, so This is important because it'll allow us to apply the mean value theorem in this upcoming theorem that we see in the book. Okay, one other issue at hand is that there are a lot of different antiderivatives. Okay? So you talk about, you know, what are we dealing with here? This is kind of a function of a function, right? So when I take an antiderivative, we kind of think of it as a function I of another function. I of f of x equals this little f of x, right? So in this particular case back here, I of, we put in what? Big F of x was x to the fifth. So it should be the other way around, right? So we're putting in this little f of x, and we're getting out this big f of x. Okay, sorry. Okay, so I'm putting in 5x to the fourth, and I'm getting out then x to the fifth. So you're finding you can also think of derivatives as functions as well. So that, you know, the derivative, a function of another function, the derivative of x to the fifth is equal to 5x to the fourth. So you're inputting x to the fifth and outputting x to the fourth. So if you think in this way, if you think of basically the antiderivative as a function, or the derivative as a function, a natural question is it really a function? Is it, you know, if I put in one thing, do I just get out one thing, or is it possible that when I put in one thing, I get out many things? And in that case, it wouldn't be a function. So, but it's kind of, you're working with functions of functions, so what the heck would be a function in that context anyways? Well, it turns out this guy over here is sort of not unique up to a certain extent. There can be other outputs. Okay? So it turns out the antiderivative of 5x to the fourth, yeah, there's one antiderivative is x to the fifth, but any constant plus that will also work as an antiderivative. Okay, so note if f, so if little f of x is 5x to the fourth, big F of x is actually not just x to the fifth, but x to the fifth plus c. So it's this thing that's a more general antiderivative. And of course we note f prime of x is 5x to the fourth plus 0. Okay? So it is truly an antiderivative. But you know, in terms of functions and that sort of thing, it's not in the traditional sense a function. This thing that we're doing, this antiderivative, is not unique, completely unique in that sense, that we put in one function and we get out one unique function. But it is kind of unique up to a constant. So if we put in a function, we're going to get out just one function plus a constant. Okay? The possible set of functions that you'll get out will just be this thing plus constant. And that's the next theorem in the book, Theorem 5.1. So it just basically settles maybe there's some question inside of you, you know, okay, I can find the antiderivative of this guy, but is that the only antiderivative? You know, or is there maybe some crazy, unimaginable antiderivative existing out there that I just am not clever enough to think up? And Theorem 5.1 says, no, not really. The only other antiderivatives will be the antiderivative plus this constant. So it says, if f is an antiderivative of f on an interval I, then g is an antiderivative of f on I if and only if G is of the form G of x equals big F of x plus some constant for all x and I where c is a constant. Okay. So we want to prove this. There's two directions for the proof. Going from the final statement to the original statement is the easiest. Okay, so this direction is the easiest. So we suppose g of x equals big F of x plus c. Thus, g prime of x must equal f prime of x plus 0, where f prime of x equals f of x. And then hence by the definition of the antiderivative, g of x is an antiderivative of little f of x. Okay, it's almost too good to be true. In the other direction, though, it's a little more work. And I use all that junk that I was saying before. Right? I use the fact that I know, so my supposition is f is an antiderivative directly from the beginning. And because f is an antiderivative, f of x is differentiable and f of x is continuous. In other words, big F of x will fulfill, if you can use the mean value theorem on it. Okay? Okay. So we'll say it fulfills the criteria of the mean value theorem in some interval I, and then we'll create an equation which is a difference between big F of x and big G of x, where big G of x is an antiderivative of f. So we're also supposing that big G of x is an antiderivative of f. So I note, or consider then this other function, we'll call it h of x, which is the difference between f of x and g of x. So f of x minus g of x. We note also one thing we'll want to have in our back pocket is the derivative of h prime of x on this interval will just be big F prime of x, which is f of x. And then because g of x is the antiderivative of f of x, this will also be f of x, which will mean in this particular interval, the derivative of h of x is 0. Okay, so from the mean value theorem, we'll pick any two arbitrary points in this interval. Let's say, let's see what variable I use in my notes. I guess just a and b. we have that there exists a C value such that H prime of C is equal to big H of B minus big H of A all over B minus A. So taking this statement and then this statement here, we can say 0 equals H of B minus H of A all over B minus A, which tells me that H of B, if I multiply both sides by B minus A, sorry, I lost you there. So I just took this statement and this statement, so I put 0 over here, multiply both sides by B minus A, and I get H of B minus H of A equals 0, which tells me H of B is equal to H of A. And then because B and A were arbitrary points in this interval, we could say H of B equals H of A for any AB in this interval. And what does that mean? That means that this thing is a constant. So hence, H of X will equal a constant for any A, B picked in this interval. In other words, because of our original definition of H of X, big F of X minus big G of X will equal C. In other words, big F of X equals big G of X plus constant. In other words, the antiderivatives, if there exists another one, supposing there exists another antiderivative, it will just be a constant, a shifted constant of the original. So the integral, so what we're going to call the integral, which we're calling the antiderivative right now, you put in a function, you basically get out just one unique function, but there's this constant issue going on. So you're not going to get any magical function popping out such that if you were just creative enough, you'd be able to find it. No, there's just one unique function, sort of. Okay, but this sort of part means there's a constant associated with it. Okay, so that's the idea. Okay. Section 2, differential equations. So we're kind of abstracting all the ideas we learned in algebra to work with functions now. So functions of functions, we're putting functions in other functions, sort of. Here we have equations of functions, and we're trying to solve for unknown functions. A differential equation has a bunch of unknown functions and the derivatives of those functions floating around. So it's basically an equation in terms of x, y, and derivatives of y. And anytime you find an antiderivative, you're really doing a differential equation. That goes over people's heads sometimes. But so for instance, y prime, or in Leibniz notation, dy over dt equals 9t squared. I want the antiderivative. I'm trying to find this unknown function y such that its derivative is equal to this. So when you're solving a differential equation, you're looking for an unknown function y. And back in algebra, you would look for maybe a number. You'd want to know this unknown variable x, right? All right, so here, how would that go? Well, our particular answer would be 3t cubed. Right? So we'll call this a particular solution to that differential equation. But we just learned, that's not the only answer. There's an infinite number of them if you include this constant plus c. And this is the general solution. Okay. Right, so we're going to rewrite this antiderivative problem now and define it as an indefinite integral. So we denote the operation of finding this general solution here. Anti-differentiation, which is, I guess, what we've been calling it all along, but we're going to say from now on indefinite integration. And we'll have a nice symbol for it. So y, in this case, equals the integral of this thing right here. So the integral symbol is this curly kind of S symbol. And then we have the 9t squared, and then we remind ourselves it's with respect to t. Right? And then the antiderivative, a particular antiderivative is 3t cubed, but then the general solution is 3t cubed plus c. Okay, so this is called the constant of integration. And we always need to include that in our answer. Okay. This stuff in here is called the integrand. And integrand. And this tells us the variable of integration. So you can integrate with respect to other variables if you want. Okay, so if you know the derivatives, you already know a lot of integrals. Okay, we're going to go through and we kind of have to learn all the rules for integrals, just like we learned the rules for derivatives. Okay, so we begin with the basic integral rules. If you take the integral of a derivative of an antiderivative, you just get back the original antiderivative, okay, plus a constant. So the integral and the derivatives kind of cancel each other out in a weird sort of way. Also then, if you take the derivative of the integral of a function, you're going to get back to where you started. Okay, so you'll get right back to f of x. Okay, so as I promised, if you know derivatives, you know integrals. So how does that work? Well, what is the derivative of a constant? The derivative of any constant is just 0. So the integral of this thing is equal to a constant. The integral of 0 with respect to x is equal to a constant. The derivative of any constant times x. The derivative of 5x is 5. The derivative of kx is k. So the integral of k is just going to pop you back over onto the other side. It's kx plus c. In general, we have a constant multiple rule, which will work for derivatives and integrals. The derivative of constant times a function is equal to the constant times the derivative of the function. And then in integral land, the integral of a constant times a function, you can factor out the constant. So you get k times the integral of f of x dx. And matter of fact, that's usually the first thing you want to do when you're encountering an integral that you don't know how to integrate, is to factor out any constants you can. Before we had that the derivative of the sum of functions is equal to the derivative, the sum of the derivatives, and that'll be true also for them, these antiderivatives. Okay, so if you're trying to figure out the integral of sum or difference of two functions, you could just consider it as two different integrals, or find the two different antiderivatives. The most fundamental rule of integration is the power rule. So remember that before we had the derivative power rule. You bring down the exponent and then subtract the old exponent by 1. The integral then is the reverse of this process. Okay. So instead of subtracting the exponent, we add the exponent, add 1 to the exponent, and then divide by that exponent instead of multiplying by the exponent. Okay, so that's our most fundamental rule. Please note, in this case, n is assumed not to be equal to 1, or rather negative 1, right? Because you put negative 1 in here, you'd have some trouble. So what is the integral when that thing is, when you have x to the negative 1? Well, you can figure that out because you know the derivative of the ln of x. The derivative of the ln of x is 1 over x, right? So the integral of x to the negative 1 dx, which is basically the integral of 1 over x dx, well, if the derivative of ln x is 1 over x, the integral of 1 over x must be ln of x. So this must be equal to ln of x, and that's true, sort of. We're going to include absolute value signs in there just to kind of extend what we'll say the domain of the values that we're looking at, extending the domain of this antiderivative. It'll make it more flexible. What else? So the derivative with respect to x of e to the x is e to the x. We know that. So the integral of e to the x is just e to the x plus c. The derivative with respect to x of sine of x is, of course, cosine x. So the integral of cosine x dx must be sine x, etc., right? So the one that always screws people up, I guess, the derivative with respect to x of cosine x is negative sine x. So when you integrate sine x, you're not going to get cosine, right? You're going to get negative cosine. Okay, so if you know derivatives, you could just reverse the process, and that gives you a whole bunch of integrals. Okay, so we want to kind of walk you through some of these. Hold on one second. Here we have example 2, the integral of 3x dx. So you can think of these integrals as a product of things, right? There's a 3 times the x times the dx. You don't want to like put the dx in front or anything like that, but other than that, you can kind of factor things. And you can factor things, constants, out of the integral. So long as it's not dependent on x, you can factor it on the integral. Okay, so here I can factor out a 3, and then I'll have x dx. And then I'm just finding the antiderivative of x. Okay. So it'll be 3 times the antiderivative of x. You go x to the 1 plus 1, and then divide by 1 plus 1. That's plus c. So this will be 3 halves x squared plus c. example 3. A bunch of parts to it. So first one, 1 over x cubed dx. Okay, we want to rewrite it so we can apply the power rule. So this is the integral of x to the negative 3 dx. And then it's, what I generally like to do is just write negative 3 plus 1, and then multiply by the reciprocal of this thing. Right? So it'd be 1 all over negative 3 plus 1 plus c. So what is this? It's negative 1/2 x to the negative 2 plus c. Let's get part B. Integral of the square root of x dx. I can rewrite that as the integral of x to the 1/2 dx. And then it's just x to the 1/2 plus 1 times the reciprocal of that. 1/2 plus 1 is, what is that? It's 3/2, right? And then if you divide by 3/2, it's the same as multiplying by 2/3. And 2 sine x dx. Let's factor out the 2 first. I'm looking for the antiderivative of sine. And that's just negative cosine. You gotta be a little careful. One more. The integral of 3 over x dx. Can factor out the 3. And the antiderivative of 1 over x is a natural log. Hey! Sorry. Let's get example 4. Ruh-roh, what is that? Well, dx is the same as 1 times dx. Right? So this just is asking for the integral of 1, the antiderivative of 1, which is x, and then add in your constant. Would be the antiderivative of x plus 2. So this one you can think of as the antiderivative of x plus the antiderivative of 2. Literally, you can write it if you want. You don't have to. Most people just do this in their head. You can write it like that. But anyways, this guy, x to the 1 plus 1 times 1 over 1 plus 1 plus 2 times the integral dx. So this would be 1/2 x to the 2 plus the integral of this thing. That's just the 1 again, right? So it's just the integral of 1 is x. Part C. So you should be able to integrate any polynomial. So we'll have 3x to the 4 plus 1 is 5 times 1/5 minus 5x to the 2 plus 1 is 3 times 1/3. And then plus x to the 1 plus 1 is 2 times 1/2, and then plus c. Some of these you have to be a little clever to figure out. So here's x plus 1 over square root x dx. We can butterfly this. Note if it was the reverse, if it was the inverse of this or the reciprocal, you could not butterfly it. You can only butterfly when you have a sum in the numerator and then a product in the denominator. So here we'll have integral of x all over square root x plus 1 over square root x. And we want to rewrite these with exponents so we can do power rules. So x to the 1 over x to the 1/2 is x to the 1/2. Subtract the exponents. Then plus x to the negative 1/2. Okay, so x to the 1/2 plus 1 is the same as x to the 1/2 plus 2/2, which is 3/2, and then multiplied by the reciprocal. Plus x to the negative 1/2 plus 1 is 1/2 multiplied by 2. So got example 6. The integral of sine x all over cosine squared x dx. This may seem like something we can't do, but if you're clever enough, you're going to be able to do a lot. So this is really sine x over cosine x times 1 over cosine x dx. Sine x over cosine x is tan x, and then 1 over cosine x is secant x. And then, depending on how well you know your derivatives, this is the antiderivative of secant. Right, so this is just secant x plus c. So we're running out of paper. I have to get up here in a second. Let's look at example 7. Integral of 2 over root x dx. Factor out that 2. So you got the integral of 1 over root x dx. Rewrite with a rational exponent. So 2 integral of x to the negative 1/2 dx. Power rule. So 2x to the negative 1/2 plus 1 is 1/2. And then divide by 1/2, which is the same as multiplying by the reciprocal of 1/2, which is 2. Let's get part B. This is part A. Part B, the integral of t squared plus 1 squared dt. We're going to have to FOIL that out. So we get t to the 4th plus 2t squared plus 1. And then it's just power rules. So this will be t to the 5th over 5 plus 2t cubed times 1/3 plus t plus c. So t to the 5th over 5 plus 2/3 t cubed plus t plus c. Oh, one more. Let's skip down to part D. The integral of the cube root of x times x minus 4 dx. So some people will try to integrate this and then integrate this, and you can't really take the integral of a product. Just like you have to use a product rule when you take the derivative of a product. Remember this? You can't just say that this is equal to cosine x, right? It's not just take the derivative of this times the derivative of this. No, you got to do the product rule. Okay? So it'll turn out with the integrals, we're not going to be able to do that as well. We'll need some sort of special product rule, which we'll learn in Calc 2. Okay? In the meantime, what you need to do is just distribute these. So x to the 1 times x to the 1/3 is x to the 1 plus 1/3, which will be 4/3, minus 4x to the 1/3 dx. And then power rules. So x to the 7/3 times 3/7 minus 4 times x to the 4/3 times 3/4 plus c. And simplify. And that's it. Okay. So to kind of get rid of this pesky plus c, one thing you could do is use initial conditions. And we'll be able to develop the formula, the position function that you see in physics doing this kind of process. So if we know the acceleration due to gravity and some initial conditions of the object, like its initial velocity and its initial position, we can find its formula for the position function. Right? It's just a process of taking antiderivatives from the acceleration. So in particular, then, we have initial conditions and particular solutions. Okay. So example 8, find the general solution of the differential equation f prime of x equals e to the x. First, find the general solution. And then secondly, find the particular solution that goes along with this initial value. Okay, so let's go at it. So first, get the general solution. That's just taking the antiderivative. Integral of e to the x, just e to the x, plus constant. Then secondly, we want to find the particular solution given this fact. Okay, so this thing right here is our big f of x. So if I plug 0 into this thing should equal 3. Right, so e to the 0 plus c must equal 3. So I'm just plugging 0 in for x into this expression. So f of 0 is 3, which is right here. And then e to the 0 is here, plus c is here. Solve for c. Okay, so e to the 0 is 1. And then c is 2. Okay, so our particular solution then is going to be e to the x plus 2. Okay, so let's take a look at the physics version of all this. And it's example 9, vertical motion. We want to develop the formula for the position function, given that we have a ball thrown upward with initial velocity of 64 feet per second. So I'll say v sub 0 is 64 feet per second. I'm also told that the initial position of the ball is 80 feet. So maybe I'm standing on a building, I'm throwing this ball upwards. So s sub 0 is 80 feet. So part A, I want to find the position function s of t. Okay, so what, right? I start with my acceleration, okay, because acceleration is going to be the second derivative. So what it then is acceleration? We're going to use negative 32 feet per second squared as our acceleration. And also note that's the second derivative of the position function. So s of t is the position function. S prime of t would be your velocity function. And then s double prime of t, which of course equals the velocity prime of t, is the acceleration function. And for us, we're going to let acceleration v, a constant, negative 32 feet per second squared. So to get to the position function, we're going to be taking antiderivatives. Okay, so if I step up one level from acceleration, I'll get back to velocity. If I step one level up from velocity, I'll get back to position. So instead of taking derivatives twice to get here, now I'm starting at here and anti-differentiating twice. Okay. So first, the antiderivative of AT with respect to t is just the antiderivative of negative 32 dt. And that'll be negative 32t plus a constant. So the problem here is we have this constant, and I need to solve for that constant. And what you do is use the initial conditions. So this formula here then is our velocity formula. And I know my initial velocity is 64 feet per second. So v of 0 is 64. And if you plug 0 in for t, you get negative 32 times 0 plus c. So c must equal 64. So that tells me, in particular, my velocity function is negative 32t plus 64. Then I want to take another antiderivative or integrate again, and I'll get to my position function. So s of t will be the integral of this thing, negative 32t plus 64 dt. So anti-differentiating, I have negative 32t to the 1 plus 1 is 2, and then times its reciprocal. And then plus 64t, and then plus another integration constant. So s of t will be negative 16t squared plus 64t plus c. And again, we want to solve for this constant. And we can do that using the initial condition, s of 0 is 80. So if I let t be 0, I'll get 80 equals, well, this will be 0, and then plus c, so c will be 80. And that'll tell me, finally, my position function, s of t is negative 16t squared plus 64t plus 80. Okay, so I think we'll just leave it at that, and thanks for watching. See you next time.